Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about our electrical safety device, fuses. So let's dive right into it. Now, we have already talked about basically ground fault detections and things of that nature, like surge protectors. Now we are looking at something very simple yet very important, fuse. So this puppy is basically in electrical definition over current protection device. If you have a scenario where you have too much current and you want to make sure that does not happen, or the basically connection is broken instantaneously or as quickly as possible, in those sort of scenario, you can rely on this puppy, fuse. Now, fuse primary job of a fuse is very simple: break the damn circuit if it's in fault condition. As simple as that. Now, how could those fault could occur? Well, you have two primary reasons. One of them is very common, simply because it can happen without you knowing it. For example, let's say you have a house wiring that is 1 square cable was used. Just go with that, and it was designed to safely handle 10 amp without any issue, and you plugged it with something like, let's say, a very simple computer. Now everything is fine, everything is dandy, everything is going YOLO, you don't even have to worry about it, you are barely touching 5 amperes of electrical load, everything is awesome. But you change that, and somehow you decided to connect a freaking giant air conditioner to that, and now everything is working, but you are exceeding the current capacity. It happened like you did anything destructive. There is an electrical plug, I connected a plug to it. So randomly over time you realize your building is burning. Why? Because that electrical wire that was designed to handle 10 ampere, you basically drawn 12 ampere out of it, it overheated, then it's basically catch on fire. Has happened with multiple equipments. So that's an overload scenario, because you could do that without realizing it. Like, you can literally have a scenario where just like, hey, all I did is like plug my iron. Now here's the deal: you could be in a scenario where your house is already almost at the breaking capacity, and the moment you plugged in, it will be like, that one final thing that broke the system. So overloads are very dangerous. It could easily set things on fire. And then you have short circuit, basically where live and neutral gets a bit too excited with each other. In those sort of scenario, you could literally set your whole neighborhood on fire, and I'm not joking about that. These things are serious, deadly. So we have to have some serious protection to fight against that. Thankfully, this basically prevention of fires and equipment damage, because your equipment is not going to survive if it's in a scenario of overcurrent, like your house wiring. And in case of like India, we have house wiring, but it's generally done inside the wall, so that means it's very difficult to replace once it gets destroyed. So to protect the equipments and all that jazz, we want to be in a scenario where it's like, dude, protect us against overcurrent scenarios. Now, generally, there is a lot of ratings and types involved here. Now, on a surface level, on bare minimum, on basic level, there are 4 things that you must understand. First is current rating. Basically, how much do you want it to allow? Because this is a braking device. It's like it applies brakes if ampere exceeds. So you would be like, hey, this is a lamp system. It's a very basic lamp. It's barely running a LED system. It's only gonna draw, let's say, 1 amp, maximum 1 amp. You're like, okay, awesome. Put a fuse that blows up at 1.5. So if you are in a scenario where short circuit happens, it's gonna go basically 10-20 amps instantaneously, and the fuse is like, nope. Let's say some bad effect happens on the system and you're drawing too much current out of it. It's like overheated, LEDs are burning out, started to draw 2, 3, 5 amps. Fuse is like, nope. So in those sort of scenarios, that's the first thing you look for, the current rating. And that's why it is very critical, and that's why you see fuses of all different sizes. And even in the same size, you can find fuses that are like 13 amp, 5 amp rating, or 3 amp rating. That is the primary reason. It's like for different use case. Basically, your refrigerator is gonna need, let's say, 13 amps fuse, and your basically lighting system barely need 5 amps. So you have to be very mindful of that. That's the first thing you have to figure out: what is the amp rating. And that's why, like, in car industry, they have made such a good effort of basically color coding everything. It's like, you're supposed to put 10 in the place of 10, you're supposed to put 20 in the place of 20. You should not mix and match. So that's the first thing. Current rating is like, it's meant to handle 20, give it 20. The moment it exceeds 20, disconnect. Do not put a fuse of 10, or do not put a fuse of 30, because if you put it 30, overcurrent will happen, and your equipment will be destroyed. It will still protect you in case of short circuit, but it will not protect you against overcurrent. So your equipment is at risk if you utilize basically overrated fuses. So that's the first thing. Then we come to another aspect, which is a bit hard to understand. It's like breaking capacity. Now every fuse, all they do is basically break the circuit. Then why the heck we have breaking capacity? Well, think of it this way: like, what is the worst that could happen in your house? You can directly short live and neutral. Most of the time MCB is going to take care of that. But what is the worst that could happen? You could literally have in your junction box, basically, that is coming directly connected from utility, that could get sorted. That could cause some serious, but you are still talking about like hundreds of amps. But what would happen if this thing was happening on a serious level? Let's say your giant induction motor that is running your elevator, that goes YOLO. You are talking some serious amount of ampere that could go through that system. In those sort of scenario, your basically the fault current would be too goddamn high. So you will go from hundreds of amps to thousands of amps. In those sort of scenario, if you do not have adequate equipment, your fuse will simply does not matter. Because, for example, let's say you have a simple glass fuse, very simple, cheap, easy, effective, easy to buy. You put that, basically the wire melted because the current is too high. Here's the deal: because the current is too goddamn high, the metal did not melt, it turned into basically plasma. Now, because it's a plasma, it's a freaking conductive, so inherently your fuse is no longer able to stop the electricity. It's like, no, I'm gonna go through no matter what. And if the it's bad enough, it could literally coat the metal, basically coat the whole system into basically conductive stuff like arc, and that arc will literally jump into everything electrical nearby, basically metal contacts nearby. So it is very serious. You have to understand braking capacity. Like in your car systems, generally everything is designed to handle the maximum the battery can do, which is very high, because if you are familiar with starter energy requirement, it's hundreds of amps. So every system in the system is designed to handle that kind of worst case scenario, because you know for a fact that battery can dump that kind of amperes. So that is the whole point of braking capacity. It's like, if you are talking about something simple, like, hey, this is all it is just an extension board, you're gonna have a basic bitch fuse. But if you're talking about, hey, this is some serious inductive load, it could have some serious fault, you're gonna utilize a basically sand filled fuse, simply because in case of a worst case scenario, you have a very high fault current, the metal is gonna melt, and then it's gonna be extinguished. The arc would be handled by the sand. So braking capacity is very interesting aspect. Then we have acting speed. Now that does not make sense, because simply the first thing you will think about, hey, if something bad has happened and current has been exceeded, deploy brakes instantaneously. It's like, why do you want acting speed? Why do you want a quote unquote slow? Simple reason is there are very things that create high current scenario all the time the moment you turn them off. For example, anything with giant transformer in it, or anything with coils in it. For example, motors have huge inrush current, like idiotically huge. If you have a sensitive fuse, it's gonna blow them every time the moment you turn the motor on. So you need a fuse that can let that go through. So you need acting speed. And for example, you cannot utilize fast acting fuses for things like inverters, UPS, things of that nature. You cannot use those there. But what about semiconductor equipment? Let's say your TV has a fuse. That's a puppy supposed to be as fast as possible, because semiconductors, they are not resilient at all. So flat out, you need idiotically fast acting speed. So that's why acting speed also you cannot mismatch. If you put a basically slow acting fuse on a semiconductor device, yeah, semiconductor is toast. If you put a basically fast acting fuse on a basically inductive load, it's gonna trip every time you turn it on. So fundamentally, you have to take that into consideration. Generally, it's very simple: fast or slow. Then AC and DC is also another aspect. Now that has become a much bigger issue for most people nowadays, simply because of solar industry, and because solar industry is such a big industry, and now every Tom, Dick and Harry has a giant solar farm in their house. DC has this ability to basically not quench the arc that it creates. Think of it this way: you have two contactors. Let's say the cable got disconnected for some reason, and you're doing it like this. You are pulling apart the conductor. Now because of AC, worst it could happen, it was in the peak. Basically, in case of India, it would be 200 volts. You have 200 volts. The moment that's enough to create an arc, awesome, everything is awesome, you have a lot of ampere going through. But here's the voltage is dropping, because it's a complete sinusoid. It's like voltage goes, so the moment you're pulling it apart, the current is basically voltage is also going down, so that stops your system. Now in DC, there is no voltage going down. Your ampere is the primary department there. In those sort of scenario, you could literally have a solar panels, giant solar panels that are like not very high voltage. I'm talking 50 volts, but yet they can have idiotically high ampere rating. You could are talking about like 10 amps, 50 amps, or even hundreds of amps. In those sort of scenarios, the moment you're gonna do this, it's gonna burn like an arc lamp. Nothing else is gonna stop it, because there is no down voltage. So fundamentally, you need a system that is designed to handle that, AC and DC. That's why you cannot mix match. And you may be like, hey, the fuse on the cars, they sound awesome, they are designed for very high amp ratings, and they can they have perfect rating, 10 amps, 20 amps, all that jazz. You can't use that, because the moment you put AC and very high voltage is simply gonna short across. And if you're gonna utilize this puppy for solar, yeah, it's not gonna do anything. So fundamentally, you cannot mix and match. There is a reason why we have different types of fuses, different categories of fuses. Now let's start with something very simple. All of you must have used it. Rewirable fuse, basically something like this. I'm pretty sure if you are watching this in India, any switchboard near you generally will have something like this. Now these are awesome simply because they are very cheap, and once they go to get blown, you can basically replace it with a good conductor. Super easy to use. Now that is the problem with this, because a person can directly replace the conductor inside. Basically you can spool another wire there. It's like you need the correct wire, and that's far more problematic than you would think, because you will think, hey, this puppy is designed for 20 amp. Here's the company designed that system as like, one size fits all. It's not precision made for your home equipment. You may be in a scenario where this fuse must blow at 10 amps. 20 amp is the maximum system. So if you over corrected it, many people do that. Like for example, let's say you are doing something wrong and overloading the system, so the fuse keeps blowing up. You may be like, hey, it only has one strand of copper there. What if I put two strands? Now your fuse is no longer protecting you, simply because you crippled it by overrating it. So if you have a wrong gauge of system, it will cause damage. For example, will it trip if you have very high currents? Yes, but if you are messed it up, let's say you could have a scenario where you have 2.5 square copper cable in your household, and your fuse wire is like, because you got so pissed off by every time having short circuit, you made it 3 by spooling it up. The fuse is the last thing that's gonna melt. The first thing is gonna melt is the wiring. So the fuse must be weaker than the wiring inside. So that is why these things are, while they do work, while they are reliable, and we have been using them for like almost a century, they do create a problem where they are ambiguous. So wrong gauges are very problematic. I did like this anchor design, which is like most plastic cases also have ceramic inside there, because you are talking about melting metal. So they have a very good rating there. It's like 0.5, use 0.5 or if you use 4 strands of copper wires, like they're very specific about that. So that's kind of awesome. So this is what we are talking about when you are talking about rewirable fuses. Now they are being phased out for MCBs and something better like precision fuses. Now I'm pretty sure most of you have seen this or used this. Now these fuses are specifically built by a company in mass production system, where it's for preset value. What does that mean? That simply means this puppy is designed for 5 amps, it's gonna blow at 5 amps. Now again, there will be a little slip there. It won't be exactly 5 amps. The moment it became 5.01, I'm gonna disconnect. Not like that, but you get the point. You buy a 5 amp fuse, you can be damn sure it's a 5 amp system. You will not have a scenario where it's like, oh no, it kept working at 6 amp but destroyed my equipment and then it blew. So you don't want that. So in those sort of scenario, it removes ambiguity. You can easily see that in basically extension cords, because that does make a lot of sense. Think of this way: extension is draining its power from a plug. That plug is a single plug, and it is giving you multi-plug out of that. Inherently, that means you could have, let's say, plug limitation is 6 amp. You could draw 6 amp on each of its plug. That means 6 into 6, 12. 12 will be directly coming out of the main plug that was only designed to handle 6 amps. So in those sort of scenario, you want a fuse like this, and you will see that in most extension where it's just simple fuse, and sole job it has is just like, hey, trip at 6. So that's why people like these things, and many equipments have that, from basically inverters, UPS, power strips, things of that nature. A lot of things have utilized this, including computer power supplies. So there is a lot of demand for this, but they do require you to have a replacement ready in case you are dealing with something sensitive. Like for example, let's say you are dealing with your computer, and your computer is like necessary for work. You must have a like spare fuses laying around, otherwise you will be in very big trouble. If you're like, dude, I have to Amazon order it, or that exact rating. Generally it does happen that if you do not have the exactly precision match set, you could be in trouble. So I would generally recommend you to look into some set like this for yourself. Generally they are available for very low cost in shops, but it's hard to find them in shop. In those sort of scenario, if you cannot find a shop where you know for a fact that you're gonna get a good set like this, I have provided Amazon link down below, where you can have like 0.2 amps, 0.5 amps, 1 amps, 2 amps, 3 amps, 5 amps, 8 amps, and 10 amps, 15 amps, 20 amps. So in those sort of scenario, you will have enough that for basically fast acting fuse requirements, the set will be ready. And generally, if you have something that requires a basically sand field system, you can buy basically sets of that also. Generally it's recommended if you are talking about anything critical, mission critical, where it's like, dude, this equipment has to be working most of the time, you should have a replacement fuse. So and rating is another thing that still is an issue with the person in charge of this, because you could have a scenario where it's like, hey, there is a inductive load, there is a resistive load. Resistive load does not require basically slow acting fuse. It's gonna like, dude, the moment I exceed my rating, trip. Awesome. Inductive load, because of the inrush current, you inherently require slow acting fuse. You could be in a scenario where instead of putting that slow acting fuse, you put a fast acting one. It did not work. So be mindful that it's removes the person making a mistake to person not paying attention. Like person has to know the type, the rating and all that jazz, and they have to, because many times the form factor could be exactly the same. You could find a 5 amp sand filled fuse that is like exactly like glass filled one, and the sand filled one could have a double rating. It's like, hey, it's like Chinese one is inherently does not have the capacity to handle a high high amp circuits. It's like, it failed. You could destroy your equipment. So there is a still ambiguity on user end. Once you have the right hardware, there is no issue there, but you still have on the user end. Now we talk about high rupture capacity systems. Basically, when you are talking about fault currents that are too goddamn high, like for example, transformers. Now these puppies can provide megawatts of power to a small block of area, and these are powerful devices. But what would happen if you have a short in megawatt kind of system? You are talking about hundreds to thousands of amp of basically electrical arc, and these arcs at this point in time becomes explosive. And I am not exaggerating that. Like electrical short circuits in those sort of scenario, power levels, they are destructive. You could literally watch hundreds of video on YouTube where it's like electrical cabinet is the strong solid metal build, they had an electrical issue, boom, like it literally went boom. So it is something very serious. People have to take this very seriously. People have lost their sight because the light is like idiotically bright. People have lost like their whole lives because of like they were in the wrong place at the wrong time. So this is something that you have to make sure that you understand. When you're dealing with a very high amp current in short circuit scenario, it could get out of control very quickly. So when you have arc that is ludicrously high, flat out from arc's point of view, everything is conductive at that point in time, so you cannot do anything. So what we utilize is high rupture capacities, basically arc quenching medium. Now depending on the company, depending on the brand, it could have a different sort of system to handle that, but generally all of them would have something that resembles a sand or some sort of filling. The idea with this filling is, with the arc quenching medium, is that you're gonna have a conductor. The conductor is gonna melt the moment the current rating is exceeded. Everything is awesome, but here's the ampere is too goddamn high. Like think of this way, 100,000 amps, it's too goddamn high. So what will happen, because the arc is created, it's so high temperature, it's gonna melt the surroundings. The surroundings in this sort of scenario is designed in such a way that it's gonna melt and turn into a glass like substance which will have ludicrously high resistance. Inherently, basically, it's not only cooling the arc simply because it's taking the energy away and phase changing from solid to liquid, it's quenching the system and inherently creating a scenario which is very difficult for electrical arc to jump across. You have to be very mindful. These things are almost like once they go basically open, electricity has to do some idiotically high power stuff to jump across this, because they cannot. Inherently they are designed in such a way. So, and because of the reaction speed, generally they are preferred over MCBs. So you could have MCB and fuses also, but generally if you are talking about something very severe, this will trip before MCB does. And you generally want this also simply because your fuse are replaceable but your equipment is not, and they can have very fast response time. I'm like 4 millisecond or even faster than that. So in those sort of scenario, these materials saves people life. And when you are talking about high rupture capacity, you will find something like, especially in substation size system or for a big building, you're talking about like 12 kV or like even like 1000 volt systems, you may find something weird. It's like, dude, why the heck this fuse has a quote unquote plunger in it? It's like, why there is a plunger? Generally that is done for 3-phase system. For example, for buildings elevator, these things are kind of common. I provided a video down below. So the idea with that is, the moment you have one fault in one phase, if you let the unbalance, basically now the 2 phases is running in a load, it will become unbalanced over basically instantaneously. You want to disconnect all of it. You have one fault, you disconnect all 3. In certain loads you have to do that. When you are talking about in those sort of scenarios, the plunger is basically triggers a disconnecting device. So you could have fault in one phase, it disconnects all remaining 2 phases, so everything is safe. You do not have like, okay, one tripped, then another tripped, then another tripped, because that does happen if you have a fuse that blew up but did not basically trip the other device, because over time that overcurrent event will destroy everything else. And you may find they are like protected with shields. The idea with these shields are, because high like these fuses, they are human made devices, they are susceptible to quality control, mismanagement or faulty rating. Heck, you may put something that is designed for, let's say, only 10,000 amps, but you're supposed to put 100,000 amp fuse. You could have an arc that could just jump through to another phase, and if that happens, God help you. So that is why we utilize high rupture systems when we need ludicrously high power to be handled safely. And I have provided Siemens video down below that is quite amazing. Like they have utilized a high-speed camera to show a cheap knockoff versus their own brand. Now again, it's a bit of a marketing also, but you get the point, like what will happen if you have a bad system. And that is why even if you are using the best company's equipment, they will still have blast shield around these things, because they do have a tendency to go boom time to time if the current handling capacity is exceeded, because again, they are devices. It's not like God built them, like it's Thor's hammer, nothing is gonna happen. Heck, even that broke. So be mindful of these things. So this was my presentation on something simple yet very important, fuses. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.